Keeping centrifugal pumps working reliably as they move fluids from one place to another requires careful monitoring of their performance, usually over an extended period of time. When pumping conditions change or when a pump ages or wears out, the changes may be indicated by three factors: the pressure or head the pump produces, the flow through the pump and the piping, and the power the pump requires during its operation. In this program, we'll show you what happens when the pressure or the flow in a pumping system changes over time, and we'll show you how the change affects the power the pump requires and the work it can do. Changes in pressure, changes in flow, and changes in power can help you spot pump operating problems before they become serious. They can help you schedule maintenance more efficiently, and they can help maintain continuous production. Careful monitoring often allows you to know in advance when a pump needs to be pulled out of service for replacement or overhauling. Let's start with pressure, or head as it is called, in a centrifugal pump. Think of head as the work a pump must do in order to move fluid through a system. The total head in a system has three parts: static head, pressure head, and friction head. Each of these are just a different kind of work that the pump must do. We'll discuss each of these in turn, and we'll show you how they are calculated. Let's start with static head. Think of static head as the weight of the fluid that has to be moved from one place to another. It's usually easier to figure static head if you calculate it on the discharge side, then on the suction side. Then add the two together and get the total static head. Let's look at an example. Here we have a simple system where the discharge side is 100 feet above the pump and the suction side is 5 feet above the pump. The static head on the discharge side is 100 feet. All this means is that the pump must do enough work to overcome the pressure of 100 feet of water. The static head on the suction side is 5 feet. But since the pump does not have to do any work to make the water on the suction side flow into itself, we subtract the suction head from the discharge head. 100 feet minus 5 feet is 95 feet. So the total static head in this system is 95 feet. At this point, you may be asking yourself, 95 feet of what? Well, the head is equal to the pressures exerted by 95 feet of water. Now, 1 foot of water exerts a pressure of 0.433 pounds per square inch, or PSI. So 95 feet of water exerts a pressure of 95 times that. 95 times 0.433 psi equals 41 psi. Pressure in psi and head in feet are just two different ways of saying the same thing. The pump must develop 41 psi, or the head equals 95 feet. Now, suppose the suction side is 5 feet below the level of the pump. In this case, the pump has to work to bring the water up 5 feet, so we have to add 5 feet to the work the pump must do. We must add the suction head to the discharge head to get the total head. 100 feet discharge head plus 5 feet suction head is 105 feet total head. An important factor which often affects static head is the weight, or the specific gravity, of the fluid being pumped. As you would expect, the heavier the fluid, the greater the head the pump must develop. The weight of a fluid is usually compared to cold water, which has a specific gravity of 1.0. A pump working against a head of 105 feet of water will not be able to pump a heavier fluid as far unless it works harder. For example, sulfuric acid has a specific gravity of about 1.4. If we put acid into this system, it would only reach a height of 75 feet. On the other hand, gasoline has a specific gravity of 0.75, so the same system would pump gasoline to a height of 140 feet without working any harder. Something else that sometimes affects static head is net positive suction head, often just called NPSH. In the system we've been describing, the pump does not really lift the fluid up the suction line. Instead, atmospheric pressure pushes it up. Atmospheric pressure, or head, is never more than 34 feet at sea level, even less at higher elevations. So if the suction line is too long, or if the fluid is too heavy, or if the pump is way up in the mountains where the atmospheric pressure is less, the fluid sometimes has a hard time getting up into the pump. Insufficient net positive suction head can cause erratic operation, noisy vibrations, and will probably damage the pump. It may require a redesign of the system. The important thing to understand about static head is that the work a pump must do can change a lot if there are changes in the static head. For example, if the level of the suction side is lowered, if the discharge side is raised, or if a heavier fluid is being pumped, the pump will have to work harder. The second part of total head is pressure head. Let's start by making very clear what we mean by pressure. In the system we were just talking about, we were pumping into and out of a tank that was open to the atmosphere, so the only pressure on the fluid was atmospheric pressure, the weight of the air. Since the pressure was the same on both the suction side and the discharge side, the difference in pressure was zero. Atmospheric pressure was not a factor we had to consider, except for net positive suction head at the pump itself. However, when the difference is not zero, for example, if the suction side is closed or the discharge side is closed, then the system's pressure head may have to be calculated in order to determine the total head. For example, if the discharge side is closed and under a pressure of 100 psi, then the pump will have to work harder to overcome that pressure. Now, remember that to convert from psi to feet, we multiply psi times 2.31. 100 times 2.31 is 231. So 100 psi is the same as 231 feet of head. To overcome the 100 psi of pressure on the discharge side, the pump must work harder, so we add 231 feet to the total head. Now, suppose the discharge side is open, but the suction side is closed and under a pressure of 100 psi. Since the same 231 feet of head is trying to push water into the pump, we subtract 231 feet from the total head. The important thing to understand about pressure head is that when a system is pressurized, the work the pump must do will change if the pressure is changed. So much for static head and pressure head. Now for friction head. Friction head is simply the work the pump has to do in order to overcome the friction of the fluid as it rubs on the pipes and valves in the system. In small, simple systems, friction head may be insignificant, but in large or complex systems, friction head is often important. The amount of friction head can be calculated from information found in tables in most hydraulic handbooks, like this one, the Cameron Hydraulic Data Book. In this book, friction losses are pre-calculated and arranged in tables. They are usually expressed in so many feet of head loss per 100 feet of pipe. Notice that the inside diameter of the pipe and the flow rate have a lot to do with how much friction head is in the system. This table, for example, indicates that a difference in pipe diameter of just 5/100ths of an inch in a quarter-inch pipe will more than double the friction head. Tripling the flow through the large pipe increases the head loss more than 7-fold. Additional friction loss is caused by the fittings and valves. Information about this part of friction head is also available from reference books. You can calculate it yourself from tables and formulas, or you can use a chart like this one. The valve or fitting is on this side, and the size of pipe is on this side. Laying a straight edge across the chart gives you a very good estimate of the friction head of a particular valve or fitting when installed on a particular line. For example, a globe valve on a 6-inch line has the same head loss as 150 feet of 6-inch pipe. Or here, at the lower end of the chart, we see that a sudden contraction in a 6-inch line will have the same head loss as 3½ feet of 6-inch pipe. To calculate the total friction head, just add up the individual friction heads of all the piping, all the fittings, and all the valves. The important thing to understand about friction head is that every foot of piping, every fitting, and every valve adds to the work the pump has to do. If old piping has rust or scale, or if a valve somewhere is stuck partway closed, pumps will have to work harder because the head is greater. That's head, static head, pressure head, and friction head. It's the work the pump has to do. Now let's look at flow, and let's start with a typical pump performance chart. This one is for a pump designed to develop 170 feet of head and deliver up to 210 gallons per minute. The chart relates the pump's head capacity and its flow capacity to each other. This is done by plotting head vertically up the side like this, and the flow horizontally across the bottom like this. The pump's performance curve here indicates how much head will be produced at a particular flow rate. For example, the performance curve indicates that this pump can produce 75 gallons per minute against a head of 165 feet. If the head is reduced to 90 feet, it can pump about 200 gallons per minute. The performance curve will be accurate if the pump is powered by a 10 horsepower motor rotating at 3,450 RPM. Changes in the speed of a pump, of course, will change a pump's capacities. For example, this curve describes head and flow capacities if the pump is operated at 3,450 RPM. And this curve describes head and flow when the pump is operated at 1,725 RPM. Notice that when speed changes, head drops off, a lot faster than flow. This is typical. In fact, in most applications, flow will drop at the same rate as the speed, but head will drop by the square of the speed. For example, cutting the speed in half will reduce the flow by about half, but will reduce the head to 1/4 of the head at full speed. While we've got the performance chart here, let's look at the third factor that should be monitored: power consumption. The power required to operate the pump at different speeds changes faster than flow or head. Reducing the speed by half reduces the power required by a factor of 8. What this means is that even a small decrease in speed can mean a large decrease in power. You can see this visually on the pump chart when you compare the total area under each of the performance curves. The area under each curve corresponds to the power required to achieve the head and flow capacities indicated by the curve. This area is just 1/8 as great as this area, so operating at any point on this curve will require 8 times as much power as operating on this curve. The performance curve for any pump describes the work the pump can do and how much power it will require to do that work. The relationship between head and flow and power is the reason why routine, careful monitoring of all 3 factors is important. Any change in one can affect the other 2 and may indicate operating problems. For example, suppose you are monitoring the system over time and you notice a decrease in flow. It could mean that the head or pressure has increased somewhere in the system. You could have a plugged suction line, or a partially closed valve on the discharge side, or a buildup of rust and scale in the piping. If there is a decrease in flow but no change in head or pressure, then the pump or motor may not be adequately lubricated, or the voltage on the motor may have changed. Now consider that your monitoring detects a decrease in pressure. This may mean that the flow has increased. A valve may have been left open, or there may be leaks in the system. If there's a decrease in pressure but no change in flow, it could mean that the pump's packing or shaft sleeve are badly worn. Finally, suppose you are monitoring the system and you notice a change in the power demand. With most impeller designs, if the system pressure is reduced, both the flow and the current draw of the motor will increase. The motor may become overloaded and burn out quickly. Sometimes, increased power demand will signal a change in the specific gravity of the fluid being pumped. If the pump must move a heavier fluid, it will have to work harder, but there may be little if any change in the pressure or the flow. Often, manufacturers provide troubleshooting guides which can be helpful in tracking down problems once your monitoring has indicated that a problem exists. Most manufacturers also supply pump performance charts so you can compare the pump's design characteristics with the actual head, flow, and power requirements at your installation. This is often helpful when trying to determine the significance of any changes over time. In this program, we've taken a close look at head, flow, and power in centrifugal pumps. We've seen how all three indicate the general operating condition of the system. And we've seen that monitoring changes in these three factors, pressure, flow, and power, may provide an early indication of operating problems. The more problems you can spot, and the earlier you can spot them, the more likely it is you'll be able to maintain continuous, efficient production at your facility.